Inside every processor, electrons flow through microscopic silicon switches billions of times a second. Every image and character you type translates into physical pulses. To understand how those physical switches calculate data, you need to be familiar with the 8-bit binary number line, where column weights double from right to left, starting at 1 and ending at 128. Today, we are looking at the arithmetic logic unit. We will calculate the sum of two 8-bit integers, identify what happens when a number gets too large to store, and use logical shifts to multiply and divide. Binary serves as the physical architecture for digital reliability, grounding abstract mathematics in the precise, unambiguous reality of electronic hardware. Because those electronic components only have two states, on and off, we only have two digits to work with, 0 and 1. That means we cannot write the number 2 in a single column. We have to carry it over. This reference chart shows the 5 basic rules of binary addition. Adding zeros and ones works exactly as you would expect. The key difference is the bottom two lines. 1 plus 1 equals 0, carry the 1, and 1 plus 1 plus a carried 1 equals 1, carry the 1. We will put those rules to work by adding the Denary numbers 43 and 74 together using a binary place value grid. Starting on the right with the least significant bit, 1 plus 0 is 1. 1 plus 1 is 0, and we write the carried 1 in a dedicated row underneath. 0 plus 0 plus our carried 1 is 1. 1 plus 1 is 0, carry the 1. 0 plus 0 plus the carry is 1. 1 plus 0 is 1. 0 plus 1 is 1. And finally, 0 plus 0 is 0. If we add up the active columns in our result, 64, 32, 16, 4, and 1, we get 117. This matches our original Denary addition perfectly. Every processor has a predefined memory limit. In an 8-bit register, the absolute maximum value we can store is 255. So what happens if we try to add 1 to it? We start with 8 ones. Adding a 1 to the far right creates a 0 and carries a 1. That carried 1 hits the next column, creating another 0 and carrying another 1. This sets off a cascading chain reaction all the way down the line. When that chain reaches the end, it generates a 9th bit, but our register only holds 8. Because there is no hardware available to store it, that final bit is dropped. This phenomenon is called an overflow error. As far as the computer is concerned, we just added 1 to 255, and the result was 0. If a software developer does not anticipate this absolute hard limit, critical programs can crash and their logic completely fails. Identifying when this error will occur is a frequent requirement in computer science examinations. Beyond addition, the processor needs to scale numbers up and down. Instead of running complex multiplication operations, the hardware uses a shortcut, shifting the bits directly. Take the binary number for 22. In a logical left shift of one place, every single bit will physically slide one position to the left. The most significant bit on the far left gets pushed out and discarded. To fill the newly vacant spot on the far right, the least significant bit, the computer pads it with a 0. If we read our new binary number, we have a 32, an 8, and a 4. Our 22 has become 44. A single left shift multiplies the value by 2. The reverse operation works the same way. In a logical right shift of one place, the entire sequence moves right. The bit on the far right drops off. A 0 fills the new gap on the left, and our total value is halved. Because any odd number will lose its final 1 when it drops off the edge, right shifts perform integer division.
The fractional remainder is simply thrown away. Every shift scales the number by a power of 2. Shift left by 1, you multiply by 2. Shift left by 2 places, you multiply by 4. Whether you are adding 8-bit integers, predicting a 9th-bit overflow, or scaling data via logical shifts, these operations form the baseline of digital logic. This document shows the March 2024 grade thresholds for Cambridge IGCSE Computer Science. Because these mathematical fundamentals are heavily tested, mastering them is critical for securing high marks on the paper. You will frequently see questions like this one, requiring you to perform a logical left shift of 3 places on a specific binary value and provide the resulting 8-bit integer. Practice these techniques until they are second nature. For step-by-step guides and more exam resources, visit studybuddy.tech.